As of late, I've been curious to know if there's anything historic under the sands of the beach near where I live. This is why I've been metal detecting along the coast to see what I can find. The overall technique of metal detecting is simple enough. You swing your arms back and forth for hours on end until this strange device in your hand goes. But if you want to get good at metal detecting, we first have to know how the metal detector works. That's why in this video, I'm going to be explaining all the fundamental components that helps your metal detector detect metal. To those of you who don't know what electricity is, it's been a vital part of our lives since the 19th century, and our further knowledge of how this mysterious force works has led us to create almost everything we know today. Our earliest concept of electricity was discovered in ancient Greece around 600 BC. The Greek philosopher Thales of Miletus discovered that by rubbing amber with animal fur, light objects like feathers would be attracted to the amber. Although this sounds nothing like what we know as electricity today, this was in fact the first discovery of static electricity. No one fully understood why this happened until 1897, when J.J. Thomson discovered that atoms contained small, negatively charged particles known as electrons. This discovery led us to the strangely named plum pudding model of the atom, where many small electrons are stuck in the surface of a positively charged atom. Although this model is greatly outdated by today's standards, it does a great job for explaining how static electricity is created.
We can recreate this experiment today using a perspex ruler, a cloth, and some polystyrene peanuts.
When the cloth and the ruler are rubbed together, some of the electrons from the cloth are transferred to the ruler. Because of the conservation of charge, the unbalanced number of electrons makes the ruler negatively charged and the cloth positively charged. To balance the charge, the ruler will attract positively charged objects towards it and transfer excess electrons to them. Although the ruler experiment doesn't show us any sparks of electricity, this machine can. Using the same method as before, the friction between the brushes and the perspex creates a buildup of electrons. In order to balance out, the electrons must travel across these two electrons to balance the charge. We call this flow of electrons potential difference or voltage, and it is what we know as electricity. This is much easier to see in things like plasma balls. A plasma ball usually consists of three components: a high voltage electrode, a glass dome, and a noble gas such as neon or xenon. When a potential difference is applied, the electrons within the electrons have no choice but to travel through the gas and into the dome, where the electrons can then escape through the air. Although the electrons themselves don't produce a glow, the noble gas that they travel through does. I discussed light more in depth in my last video, so if you want to know more, then please check it out. When we look at the flow of electrons inside the electrode, we don't see them flowing in one direction. Instead, we see them flowing back and forth. This is what we know as alternating current. For now, we're only going to look at how we create an alternating current. To understand how we do this, we first have to understand how we produce energy for our homes. Most sources involve converting kinetic energy into electrical potential energy, and to do this, we need a generator. Creating electricity is surprisingly simple, and all you need to make it is something that almost everyone can find in their house: magnets. Magnetism can occur when the electrons inside a metal become aligned. This can sometimes occur naturally in the form of magnetite. When we look at the atomic structure of a normal piece of metal, we can see the electrons inside the metal are misaligned and don't add together. However, if the electrons become aligned, the spin of each electron will add up and cause the electrons to oscillate in harmony. This movement creates a magnetic field. We can think of this as like running a comb through hair. We straighten each individual hair so we look nicer and attract things more. In a generator, for example, a coil of wire is spun between two magnets with opposite poles facing the coil. As the coil rotates, the electrons interact with the magnetic field from the magnets. This pushes the electrons through the coil like pushing yogurt through a frube. Because the coil is spinning, the directions that the electrons are pulled changes every half turn. This is how we create an alternating current. When we look at an alternating current in a wire, the oscillation of the flow of electrons mimic that of a permanent magnet. So if magnets can induce the movement of electrons, then the flow of electrons should be able to create a magnetic field. This is what we know as electromagnets. We use this property in many different applications like induction cookers, where the alternating magnetic field excites the metal pan and creates heat through natural resistance of the metal. This method of exciting metals is exactly what we see in the metal detector, albeit with less heat. In the case of the metal detector, an alternating current is passed through the coil of wire to create an electromagnet. When this electromagnet moves over a metal object, the magnetic field emitted causes the metal object to create a magnetic field of its own. This magnetic field is then detected by a receiver coil and is registered as a small beep from the metal detector.
Some metal detectors like this one can be able to detect between two different materials based on their conductivity. Something is detected by the detector, it will give a number based on its conductivity. As we can see, if I scan this wire in my garden, it gives a high number around 30. This is because it's the copper wire that's leading to my shed. although I'm definitely not digging it up. I didn't detect the bells on my cat's collar. Oh, what? Huh? What? Okay. To put this to the test, I will be detecting between 3 different materials that I have found. The first material being a piece of aluminium, the second material being a piece of copper, and the third material being a Saint Laurent bracelet that might just be a fake. When we scan the copper, we get a reading near 30. This matches the high level of conductivity that copper has. If we detect aluminium, we also get a high number in the 20s. This also demonstrates the high conductivity of aluminium. However, when I scan this Saint Laurent bracelet, it gives me a low reading, around about 10 or 12. This is much similar to this colander I have, which just happens to be made of stainless steel. Once you understand how each of these metals react on the metal detector, it's surprising just how much you can find on any old beach.